So now we're going to look at a couple of facts which give us a way to think about the idea of linear independence geometrically. What does this imply about the way the vectors look like? So we're going to start with the case where we've got two vectors. So we've got a set containing two vectors. And if you start with the assumption that they are not linearly independent, so in other words, they are linearly dependent, it turns out that means automatically, that's already enough to imply that one of them is a scalar multiple of the other. And well, let's take a look at why that's the case. Let's suppose that they are linearly independent, or that the set S is linearly dependent. So what that means is, it means you can write a linear combination C1U plus C2V is equal to 0. So you've got a vanishing linear combination where at least one of the weights is not 0. So let's say with C1 and C2 not both 0. Okay, that's all you can really say for sure based on the definition of our assumption that the set S is linearly dependent. So, okay, well, let's consider two cases. There's two cases to consider here. Case 1 is that C1 is not equal to 0. Then, well, regardless of whether C2 is 0, because we're not going to make any assumptions about C2 here. It might be 0 or it might not be 0. But regardless of whether it's 0, if C1 is not 0, we can do this. We can say C1U is equal to negative C2V, right? Just take this term and fire it over to the other side of the equation. And that then you can take, now I can take both sides of the equation, multiply it by 1 over C to get U is equal to negative C2 over C1, all multiplied by V. It's safe to do that because we've assumed we're in the case where C1 is not equal to 0. So if C1 is not equal to 0, then it's okay to multiply both sides of the equation by 1 over C. And then that brings you here. Well, what does that tell you? It tells you that U is a scalar multiple of V, right? Just what is the scalar? Well, it depends on what C1 and C2 were, but you can figure it out in this fashion. So that means in that case, the proof is complete, right? We know that one of the two vectors U and V is a scalar multiple of the other. The other case might be, though, is that C2 is not equal to 0. And maybe you want to pause the video and see if you can fill in the rest, but it's going to be the same sort of approach. If C2 is not equal to 0, well, then we'll just move the other term over to the other side of the equation. So we'll leave C2V where it is, and then we'll subtract C1U from both sides of the equation, and that brings you here, and then you can multiply both sides of the equation by 1 over C2, and you get V is equal to negative C1 over C2 multiplied by U, and that's, again, that satisfies the equation, right? Or not the equation. That satisfies the statement because in that case, then V is a scalar multiple of U, and that's enough to say that one of them is a scalar multiple of the other. So I'm going to put a box here that completes the proof. And if you're wondering, well, what about the case where they're both equal to 0, or pardon me, where they're both non-zero? Well, then you could do either of these. You could do either of these arguments would work in that case, so there's no need to consider that as a separate case. Okay, and the reason I've squished this all into the top here is because I want to leave room to draw a picture. So if we were dealing with two-dimensional space, which is kind of the easiest one to think about, then you'd have a situation like this, and I'll put another copy over here. Let's draw what two vectors in R2 that are linearly independent might look like. So I'll draw one vector here, and then I'm going to do the other one in green, actually. So let's say I have the other one in green here. That's what the situation may look like if you've got a set of two vectors, U and V, that are linearly independent. In other words, they're not scalar multiples of each other. They don't point in the same direction, and they don't point in the opposite direction. But if you had two vectors that are not linearly independent, or in other words, they are linearly dependent, well, that might look something like this. I'm just going to try to draw. I'm going to draw the vector V as if it's a longer vector, but it's like it starts from the origin as well, but the U is only covering up part of it, so you could see it emerging behind. I'm just trying to draw it be the same a vector with the same direction, but just a little bit longer than u. But the main idea here is that these two vectors are scalar multiples of each other. So this is what the picture might look like if they're linearly dependent. And actually, the way I'm saying this, I'm saying it is a set. So the set itself is linearly independent. Or in this case, it would be linearly dependent. I think I mentioned this already, but if you can say that the vectors, plural, are linearly independent, or you can say that the set of vectors, singular, is linearly independent. And if you get it mixed up, that's not the end of the world. But okay, so that's what the case would look like with two vectors. Let's talk about maybe three vectors. What happens if you have three vectors? So we've got a set S consisting of three vectors, u, v, and w. We're not going to make any assumptions about what dimension they live in. But if that set of vectors is linearly dependent, then what you know is that one of those vectors, u, v, or w, you don't know which one necessarily, and it could be more than one of them, it could be all of them actually, but one of them is a linear combination of the other two, guaranteed. So let's look at why that's the case. And the argument's similar. So we're going to suppose that we have C1u plus C2v plus C3w is equal to 0, with C1, C2, and C3, not all of them are 0. How do I know to start out that way, by the way? And similarly, how did I know to start out this way? I'm just unwinding the assumption. What is the meaning behind the assumption? The assumption here was that S is linearly dependent. This is what that means. It means you could possibly do this. And if, in this case, S is linearly dependent, well, you've got three vectors. So it's the same thing, except now you have three weights instead of two. Okay, so from there we have to show that one of them is a linear combination of the other two. Well, you can do this in the same fashion as before. Consider cases, right? You know at least one of them is non-zero. So simplify things by considering cases. So case 1 would be that C1 is not equal to 0. Well, if that's the case, then we can say, okay, C1u is equal to negative C2v minus C3w. And from there, you can say that u, I'm going to multiply both sides of the equation by 1 over C1, which again I can do because I'm in the specific case where C1 is not equal to 0. And that's going to give me negative C2 over C1 times v plus negative C3 over C1 times w. And guess what? That means u is a linear combination of the other two vectors in the set S, which are v and w. So in that case, the problem is solved. Now I'm going to do something kind of like the previous example. I'm going to say case 2 is when C2 is not equal to 0, and case 3 is when C3 is not equal to 0. And if you go back up to the previous case, like what was the difference really? It was really just a permutation of the same argument. We did the exact same strategy, but we were just considering different variables because we had to sidestep a certain issue of the fact that you can't divide by 0. So you have to be careful. Well, we don't know necessarily which of the coefficients is non-zero, but no matter which one it is, once we figure out which one's non-zero, we're going to do the exact same argument. That's no different here. Case 2 and 3 are going to be the same idea. In case 2, you're going to write v as a linear combination of u and w. And in case 3, you're going to write w as a linear combination of u and v. But in either case, the argument is going to be very similar. So I'm just going to write a little comment here and say this is handled in a similar fashion. And I'll leave it to you to fill in the details. And you can complete the argument and make it a bit more rigorous. But it's not any different than the argument we did in case 1. So I'm going to just say in a similar fashion and put a box here to indicate that the argument is done. Okay, and just like before, we're going to take a look at the picture but this time I'm going to look at a picture in 3 dimensions, because this is actually really illuminating in terms of when you're thinking about 3 vectors, what does it mean for 3 vectors to be linearly independent? The 3-dimensional case is really what you want to be thinking about. So let's say that I've got, okay, what I'm going to do here is I'm going to start by just drawing 2 vectors, u and v. And I'm going to draw u and v so that they're not parallel. Okay? even though that's not the most general possibility, but it's possible that they could be parallel. And I'll let you think about what the case would be, what the outcome would be in that case, whether S would be linearly independent or not. But if, let's say they're not parallel, well, then they're going to determine a plane, which I'm going to try to sketch here by drawing a parallelogram. I think that looks not too bad. And then I'll shade it in with my highlighter here. So that, let's say you got the vectors u and v, and you forget about w for the moment, and you just sketch them in R3. Well, remember, two vectors that are not parallel in R3, they determine a plane. And you can kind of sketch it in this fashion to kind of give an idea of its orientation. Okay, well now, what I'm going to do, and I'm going to make a copy of this picture because we're going to draw two different things that may happen. So one of the possibilities is that the vector w shoots up and is kind of above this plane. Okay, so it looks something like that. And I'm going to put my artistry to the test here and say, okay, well, if it's above the plane, it'll kind of cast a shadow here, which I'll try to draw in gray to really make it clear that that's happening. And then I'm going to draw a dot here and then indicate that that leaves a right angle. Okay, so I'm hoping that really captures the idea where this vector w, it kind of shoots up at an elevation and shoots away from the plane. It's not contained within the plane. So remember what the plane is that I drew. That plane that I shaded, that's the span of u and v, which is the set of all linear combinations of u and v. So if w shoots up from the plane and kind of points away from it and is not inside the plane, that means w is not in the span of u and v, which means it's not a linear combination of u and v, which means u, v, and w are linearly independent. So this is kind of the case you should think about in your mind when u, v, and w are linearly independent. Okay, and another possibility though is that w is in the plane, and if you were to draw a picture of w, it wouldn't shoot up and away from the plane, and it wouldn't have that gray shadow, and it wouldn't have that this is trying to capture the distance away from the plane, but that distance would be 0 in this case over here. If the vector w was contained within that plane and it was right inside there, well, that distance would be collapsed down to 0, and there would be no distance there. Well, in that case, w is in the plane, which means w is in the span of u and v, which means w is a linear combination of the vectors u and v, which that's the picture you should have in mind when u, v, and w are linearly dependent.